Okay, so let's go ahead and go through problems 3 and 4. For problem 3, I can clearly see a quotient, so I want to maybe make a little reminder of what the quotient rule is. And I have two divided functions, and I'm differentiating them. We're going to get a quotient, and the numerator looks a lot like the product rule, f prime g, f g prime, except that it's separated by a minus instead of a plus. And then all of that is over g squared. Okay, so we're going to use the quotient rule. All right. One of the ways to set this up, that's maybe I'll look at this a different way than we did in problems 1 and 2. Instead of writing these derivatives as placeholders in line, I could also say, okay, my function f is sine of x squared. My function g is x squared, and I can compute what are the derivatives, what is f prime and what is g prime. Okay, g prime is easy, that's just 2x. F prime I have to be a little bit careful with. Sine of x squared, there's no parentheses here. But if I wanted to square the sine function, our shorthand for that is putting the squared right on it. And if I didn't, then I would put parentheses around the sine function. Okay, so it's just the x that's squared, not the sine function. So if you want to be clear about this, you could put the x squared in parentheses, although it's not strictly necessary. So when I differentiate this, I can see, okay, the x squared is my inside function. So this is a chain rule. So I differentiate the outside. The derivative of sine of stuff is cosine. Plug the inside function in, and then multiply by the derivative of the inside function. So that's 2x. Okay, so when I'm looking at my quotient rule, f prime g minus f g prime all over g squared, I can just copy these pieces over. So cosine of x squared times 2x, I'm going to write the 2x in front. Just think that's a little bit nicer looking. And then I put the g function in, that's x squared. And we put the f function in, sine of x squared. And then we put the g prime in there, 2x. Okay. Now in our original problem, there was no parentheses around the x squared, but there was nothing else going on in the numerator. Okay, it was just sine of x squared, nothing else. So we were pretty safe by assuming the parentheses there. When you have other multiplied pieces, though, you really want to have parentheses to indicate what's inside the sine function and what's not. Okay, so even though the original problem didn't include parentheses, going forward, we should make sure that we always include them because we have more pieces, right, more multiplied factors going on. All right, and then divided by g squared. The g function is x squared, which is then squared. Okay, and I'm going to take a step to clean this up a little bit. X times x squared will give me x cubed. So we have 2x cubed times cosine of x squared minus 2x times the sine of x squared all over x to the fourth. And we could simplify further. You can factor, there's a 2x common in the numerator that you could factor out. In particular, if you factor out an x, you could cancel it with 1 in the denominator. Okay, keep in mind the stuff inside the cosine and inside the sine, that can't move in and out. So I can't factor that x squared out. I can't cancel that. Nothing goes in and out of trig functions. Okay, so that's fully simplified. All right, problem 4, we have a cosine function that's inside the log function. So I'm going to use the chain rule. And I'm differentiating a log function. So just as a reminder, the derivative of natural log of x is 1 over x. If I take the derivative of natural log of some function, maybe I'll call it u, then I get 1 over u times the derivative of u, or we usually just write it as u prime over u. Okay, so when I differentiate here using the chain rule, I have natural log of some function, so I'm going to get u prime over u, so the derivative of cosine x, which is negative sine x, over the inside function, over cosine x. Okay, so I can just write that as negative sine x over cosine x, or you could even write that as negative tangent x. That was a quick one, but it's easy to make mistakes on that. Any questions over derivatives? You know, derivatives seem like there's a lot more to it when you did Calc 1, and there is, but you know, this is our quick review. All right, let's go ahead and look at integration. These first two are basic integrals, okay? So the first one, we're just going to use a power rule. You just have to set it up correctly. The second one, remember that an integral is an antiderivative. So if you can look at something and say, oh, that's the derivative of something I know, then that's what you use to do the integral. So for 6, that's what you're going to do. You're going to look at that and say, ah, I know something whose derivative looks like that. Okay, so go ahead and try these. We'll just give you a quick minute. These 5 and 6 should be quick problems. And then we'll move on to the harder review. All right, let's go ahead and take a look at problem 5. I'm going to start by rewriting the problem. So square roots we can write as you know, a fractional exponent, so I can write that as a half power, but it already has a power on it, so we're going to make a fraction out of the power. So I'm not going to start by integrating. I'm going to start by rewriting this as x to the 3/2 power. So I'm integrating 4x to the 3/2 dx. The 4 is a constant multiple, so it's just going to hang out while we integrate. And what I'm going to do now is use the power rule for integration. So I add 1 to the power. So 3/2 plus 1 is 5/2. And then I divide by the new power. So you can write divided by 5/2. I always like to, right away, instead of creating a fraction inside of a fraction, I like to change it to multiplying by the reciprocal 2/5. Okay, but if that's confusing, you just write divided by 5/2 and leave that for another step. Okay, when we integrate, we always get our plus c. And that's basically it, right? This is just 8/5 x to the 5/2 plus c. And we're done. Okay, for problem 6, what we have to do is remember the derivatives of our trig functions. The derivative of tangent x is secant squared x, and the derivative of secant x is secant x times tangent x. Okay, what we have is secant x times tangent x. So I can say, well, the derivative of secant x is secant times tangent. So going the opposite direction, if I integrate secant x times tangent x, I will get secant x. Okay, assuming that your trig functions are defined using radians. If they were defined using degrees, then we have this crazy factor that pops out. It's pi over 180. Okay, so just if it's not written, we assume everything is in radians in calculus. All right. Let's look at questions 7 and 8. On questions 7 and 8, I'm going to throw a reminder right away from the beginning. We don't have a product or a quotient rule for integration. Okay. Number 8, we don't have a quotient rule. So I will definitely post this after it's completed. So the blank one is up right now, and I'll post this as soon as we're done. Yeah. All right. So for 7 and 8, there is no product rule for integration. Right? For 8, there's no quotient rule for integration. Later on in, I think it's chapter 3, we will look at some way to do an integral that involves a product, but that's not something we would want to use here anyway. Okay, so it's really complicated, and it's for other stuff. So what you need to do in this case is rewrite the integrand so that there's no more product, right? Same thing with number 8. You need to rewrite it so that there is no more quotient, and that's how you're going to integrate these. So I'll give you a minute to try it out, and then we'll go over it together. All right, let's go ahead and go through these two. The key with the first one, I want to not have a product. So before I integrate, I'm just going to go ahead and distribute this x so that I don't have a product anymore. So I'm just doing algebra stuff. I'm not doing any calculus, no integration yet. X times x squared is x cubed. X times negative 4 is minus 4x. And now the thing that I want to integrate, right, my integrand doesn't have any products. It's x cubed minus 4x, and I can integrate that using the power rule. So we add 1 to the power, divide by the new power. Okay. For the minus 4x, the minus 4 hangs out. When I integrate x, I add 1 to the power, so it's an x squared, divide by the new power. Okay. After I integrate, I don't write the integration symbol in the dx, but I do write a plus c. Okay, so there we go. Or to write it more cleanly, 1/4 x to the 4th minus 2x squared. All right. Number 8, similar idea. I need to rewrite this so that there's no quotient. There's nothing I can distribute to get rid of a quotient. But I know that 1 over cosine x is secant x. So 1 over cosine squared x would be secant squared x. So I can rewrite this as the integral of 5 secant squared x dx. And just a minute ago, we said, oh, if I take the derivative of tangent x, I get secant squared x. So if I integrate secant squared x, I'm going to get tangent x. Okay. And then we're just done. That actually works out nice, right? A secant squared we can do. If it's just a secant by itself, that's a hard problem. It's doable, but it's pretty tough. We'll do this. We'll do it later. You could do it now, but you have to be a little bit clever. So we'll wait on that. Okay, problems 9 and 10 should not be very tricky. 9, again, we got to rewrite it so there's no quotient. And then 10 is going to be the first of our u substitutions. So that's my little hint on number 10. You need to use a u substitution there. So go ahead and try those two out. We'll see what you get. I'll give you a couple minutes. Okay, let's go through these two. These two shouldn't be very challenging. Once you rewrite number 9, it should go fairly quickly. So when we had roots, we write them as fractional exponents. When you have an x in the denominator, you can write it as a negative exponent. So this is the integral of x to the negative 5th dx. And then again, I'm just going to use the power rule. So I add 1 to the power. Negative 5 plus 1 is negative 4. And then I divide by that new power, right? That's my power rule for integrals. Okay, so I can leave it like this, that's fine. Or if you want to rewrite this, it's a negative, there's a 4 in the denominator, and I can rewrite that x to the negative 4 as an x to the 4th in the denominator. Okay, so that's correct also, right? Either way is perfectly acceptable to write that. Okay, number 10, we're going to do a U substitution. And I'm not going to reteach a U substitution, but hopefully, if I do an example here, it'll come back pretty fast if you don't already remember it. Okay, so typically we want to let U be the inside function. And here I can see, well, I have an exponential with an x cubed on the inside. So I'm going to let U equal x cubed. And then we always need to figure out what the differential is. So when I differentiate this, du dx is 3x squared. Okay, I split the du and the dx up, so I multiply both sides by dx. So du is 3x squared dx. I have an x squared times dx in the problem, but I don't have the 3. So just divide both sides by 3. So 1/3 du is x squared dx. Okay, so this x squared times dx can turn into a 1/3 du. So I'm going to rewrite this now as the integral. The x squared dx is going to become a 1/3 du. And e to the x cubed, we said x cubed is u, so I'm just going to turn that into an e to the u. Okay, and constants just hang out. So the 1/3 is just going to hang out. And when I integrate e to the u du, I just get e to the u. Right, and then our plus c. And then we substitute back, right? We started with x's, we should end with x's. U is x cubed, so we get 1/3 e to the x cubed plus c. Okay, so that's U substitution, right? That should be, right at the end of Calc 1. So maybe it's the freshest in your mind, I don't know, but it's also I think the most complicated integration stuff that you've probably done so far. All right, so if you have any questions on that, you can either ask out loud or you can message me, but these next two, are going to be a little bit more in that vein, although not everything is a U substitution. So go ahead and try these two out, see what you get. These should be more challenging, I think, than the last two. So if you're getting stuck on number 11, I'll give you a hint there. It's not actually a U substitution. So 11 is a little bit of a trick. You got to do take advantage of inverse trig functions. 12 is a U substitution. Okay, so let's look at problem 11. Let me just give you a quick review. The derivative of arctangent x is 1 over 1 plus x squared, and that's what we're going to take advantage of here. So this 4 is a constant multiple, so I can just factor that out. So then when I integrate 1 over 1 plus x squared, because the derivative of arctangent of x is 1 over 1 plus x squared, the integral of 1 over 1 plus x squared dx is going to be arctangent x. Okay. You might also see that written, or you could write it yourself, as tangent with a little -1 on it, x. I try to avoid this when we're doing calculus because it can get confusing. The -1 here does not mean a -1 power. Okay. That's confusing because, like back here, right, when we wrote secant squared, that does mean a power of 2, but when you write a -1, it does not. And that's not really good notation. That's not really consistent. So I don't like writing that for inverses. I prefer the arctangent, and it's a little more clear. However, this is a common way to write an inverse trig function. So just a reminder, tangent -1x is arctangent of x. Tangent -1x is not tangent x to the -1 power. Okay, so that means that it is also not 1 over tangent x. Okay, so just remember that, be aware of that, and try not to get yourself confused. All right, for problem 12, this is a definite integral, and we have to do a u substitution. Okay, so there's more than one way to do, definite integrals when you're doing a u substitution. I'm not going to go over both of them right now. One method, the first method that I won't do right now, is you just sort of ignore the fact that it's a definite integral. You just do all your integration, and when you get back to x's, then you say, okay, I have these limits of integration. I'm going to go ahead and plug them in. Okay. The second way to do that is to say, well, when I change from x's to u's, I can change my limits of integration from x values to u values, and keep going with that. And that's what I'm gonna do here. So there is more than one way to do this. So if this looks different than you remember or what you're used to, that's okay. You use the method that you're more familiar with. All right. I think this is a little bit of a challenging u substitution because it's hard for me to see that there's an inside function here. All right, I see the fraction, I have e to the x. I say, well, x is inside the exponential. But if you ever do a u substitution and you let u equal x, all you're doing is you're relabeling the variable. So you're going to get this exact same integral, except your x's are going to be u's, and you're not going to be any closer to the answer here. What I'm going to do is I'm going to let u equal the whole denominator. So it's not really clear that I have an inside function, but if you think of this as a reciprocal function, like 1 over stuff, then that's the inside. So the idea of letting u equal the inside function doesn't always work. It's not always like the greatest strategy, or it's not the most obvious way to pick things. It's usually a good start, though. Okay, so let's try it out. U equals e to the x plus 1. I'm going to differentiate both sides. When I take the derivative of e to the x, I get e to the x. When I take the derivative of 1, I get 0. So du is e to the x dx, and I do indeed have e to the x times dx in the problem, so I can replace that with a du. So I can write this now as an integral of this e to the x plus 1 is going to become a u, so I have 1 over u, and the e to the x dx becomes a du. Okay, now I'm going to be a little bit careful here. The limits of integration that I started with were x values. I'm going to change them over to u values. So when x is equal to ln of 3, then u is e to the ln of 3 plus 1. And exponentials and logs are inverses, so when you compose them, they cancel. So e to the ln of 3 is just going to be 3. Okay. So when x is ln of 3, then u is equal to 4. When x is negative ln of 3, then u is e to the negative ln of 3. And I have this negative in the way, so I don't have exactly composed exponentials and logs. So I'm going to move this negative. Think of it as a negative 1 power. And I know that one of my properties of logs is if I have ln of x to the r, you can bring the r down out front. Right? I'm going backwards. I'm going to say, oh, I have something in front of the log. I can bring it up as an exponent. So if I think of this as a negative 1, I can bring it up and write it as an exponent of the 3. So this is e to the ln of 3 to the negative 1. And now the e and the ln are nicely composed. They cancel, and I just get 3 to the negative 1, which is 1/3. Okay, let me erase this log rule here, so I'll get myself confused. And let's go ahead and integrate. Now I'm integrating 1 over u du. I know that the derivative of natural log of x is 1 over x. So when I integrate 1 over u du, I'm going to get natural log of absolute value of u. Normally I would write the plus c, but in this case I have a definite integral. So instead I say, okay, I want to plug in the 1/3 and the 4. So I have ln of the absolute value of 4 minus ln of the absolute value of 1/3. And you can just leave it like this. That's perfectly fine. Although this does simplify quite a bit. And it's strange, but it actually simplifies to be ln of 3. And that's a little bit confusing, but it works out nicely. Okay, so we'll just leave that like that for now. All right, any questions over this worksheet? Okay, so this worksheet is all stuff that you learned back in Calculus 1, and that's going to be part of what we're doing this week. But the main stuff we're doing this week is getting started in Calculus 2. If you think back to the structure of Calculus 1, right, you started by learning limits because that's kind of the foundation for everything. Then you learned what is a derivative, and you spent a chapter learning how to do derivatives. And then you said, okay, now we'll do a chapter on applications of derivatives. Okay. Then you took a chapter on, okay, what is an integral and how do I compute integrals? Okay, and that's where you left off in Calc 1. So the natural next step is, all right, now what can I do with integrals? What are the applications of them? So that's what we're doing here, is we're sort of continuing where Calc 1 left off and looking at applications of integrals. Okay, so the thing is, integration is a little bit more complicated than differentiation. So our application section doesn't hit the ground, I think, quite as neatly as derivatives did, right? Derivatives, you can jump into these complicated word problems right away, and you already have all the derivative rules you need, and everything is nice. The problems are hard, but you can solve stuff right away. Here, we have to be a little bit more careful. So we want to start by saying, well, the whole motivation for an integral was area. So we start with area between two curves, which isn't very complicated. But we want to make sure that we have that down, because what we want to do is build up to volumes, and volumes are complicated. Okay. What we're going to be doing in this chapter is very specific volume. The volumes that we do in 2.2 and 2.3, and these are the only volumes that we're doing in this class, are of something called a surface of revolution. So it's very specific examples. We're not looking at the volume of just any old object. Okay. We can, but it's more complicated. So we want to build up in little steps. We start with area, then we look at these special cases of volume that are a little bit easier to compute. We don't actually get to general, computing the volume of any old object until Calculus 3. It's just integration's hard. Okay. So that's where we're starting this week. We're looking at areas and volumes, and then we'll keep building from there. We'll look at arc length and in the plane, and we'll keep building up applications. Okay, but the applications, if they seem a little bit more mathy and they seem a little bit less, applied than they did for derivatives, that's because we have to kind of take baby steps because integration is a more complicated process. So everything is a little bit slower, right? Building up to the applications, it takes a little bit more time. So that's what we're going to be doing in chapter 2 over this week and next week. So make sure that you jump in, watch the videos. Remember, when you watch a video, this is not like watching YouTube or TikTok. You don't sit back in your chair and watch. You should have a pencil and paper in hand when you're watching, right? You should be taking notes as you go, working examples along, right? Maybe pause and try to work out the example on your own as you go, and then you try the homework problems, right? And it starts with some true falses, right, and jumps into computing stuff. Okay, so we don't have another class meeting this week. You can feel free to email me with questions or anything like that. When you're doing the homework, another thing that you have at your disposal, every homework question should have this message instructor button on it. And when you hit that, what it does is it sets up an email to me where I can see what problem you're working on. So you don't have to type out the problem. So you can type a question here, right? Or it doesn't have to be a question. You could be a statement like, I'm confused. How do I start this? That's fine too. So if you have something quick, you can just send this. It'll send off an email to me, and I'll reply. If you're really confused, if you're like, I don't understand anything in this section, then maybe it's better to send me an email and say, hey, can we set up an online meeting and where you can explain this to me in more detail? Okay, and I'm happy to do that. I'll go nice and slow and give you a lot of detailed explanation and try to make things really clear. Okay. All right. Okay, does anybody have any questions? All right, then I think that you are set up to be successful in your first week. Oh, what was that?
I have one question.
Yeah, go for it.
I did miss the first like 8 minutes or so, so if you went over it, I apologize. But when it comes to the homework on Blackboard, will it be a situation where, like, do we only have like one shot at the homework by chance, or is it we have multiple chances at it?
Yeah, so that's a good question. Let me go through and look at this again. So let's suppose I'm doing this problem. Oops, I didn't actually write. All right, so I'm just going to mark something, and I got it wrong. Now I noticed this wasn't true yesterday. Somebody brought it to my attention, and so I fixed it. What happens is if you get something wrong, you should be allowed to get a similar question, and you can retry the question. Okay. So you should always be able to get 100% on your homeworks, right? You can retry it. Some of the questions also have help in there, like here's a link to the textbook, here's a video, right? That might explain some of this. I don't know. But when you're doing questions, suppose I'm doing this one. And I get everything wrong, you can hit get similar question and you can try it again. Now, some of them also allow you to submit again, right? So maybe I just made a typo or something like that, and I said, oh, that should have been a 1, right? And I can hit submit question again, right? Maybe that should be a 4, but at some point, it should stop letting me submit questions, right? Oops. I think it lets me submit everything. There's only so many times it'll let me. At some point, it won't let me change my answers anymore, and I have to reload the question, and it'll be a different problem typically. But you can hit that get similar question to reload it, so you don't have just one chance on the homework questions. Okay, any other questions? All right, if anything comes up, feel free to send me an email. I'm also going to set up something where you can text me questions through something called Remind. I'll post an announcement about that. You don't have to use it, but if you like it, it'll be available. So that'll be for text messages. Otherwise, I will see you again online next week. I'm going to post the recording of what we went over today. It's exactly what we